Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Possibility Trees and the Multiplication Rule. Remember to be an active learner as you watch this video. A tree structure is a useful tool for keeping systematic track of all possibilities and situations in which events happen in order. The following example shows how to use such a structure to count the number of different outcomes of a tournament. And this actually sort of applies to tournaments like the World Series. Teams A and B are to play each other repeatedly until one team wins 2 in a row, or a total of 3 games. One way in which the tournament can be played is for A to win the first game and B to win the second, and A to win the third and fourth games. Denote this writing by A, B, AA. But anyway, the question that's being asked is, how many different ways can the tournament be played? Well, let's look at that. The possible ways for the tournament to be played can be represented by distinct paths from the root, the start, to the leaf in a tree. And the leaf is a terminating point, and the root is the starting point. And the tree is drawn sideways here, and the label on each branch indicates the winner of the game. So for example, in game 1, A can win or B can win. And then we have game 2, A can win and B can win. Now notice that this one terminates because A won 2 games in a row. So that's the way the tournament rules. So that ends, but then if B wins, the tournament goes on. And if you look at all these different possibilities, you can see that we can have 1 game, 2 games, 3 games, 4 games, and 5 games are possible in order for someone to win the tournament. Now, and you should be able to recreate this kind of a drawing. The fact that there are 10 paths from the root of the tree to its leaf shows there are 10 possible ways for the tournament to be played, and that is the answer to part A. And I list a whole bunch of these ways, but you're just going from root to the ending leaf. The least number of games that can be played to determine a winner is 2, and the most that will be needed is 5. Now, B is the second question, though. Assuming that all the ways of playing the tournament are equally likely, what is the probability that 5 games are needed to determine the winner of the tournament? Okay, since they're all equally likely to happen, then all the possible ways are assumed to be equally likely. The listing shows that 5 games are needed in 4 cases: 1, 2, 3, and 4. And there were so these are the times when 5 games are needed. And so the probability 5 games are needed is 4 divided by 10, because there were 10 different paths that you could take. There's variations on this. My daughter played softball, and they frequently had double elimination tournaments. So double elimination tournament is a type of elimination tournament in which a participant ceases to be eligible to win the tournament if they've lost 2 games or matches. And that's different than a single elimination tournament when 1 defeat means you can't continue. Now, and here, well, okay. So as with single elimination tournaments, most often the number of competitors is equal to a power of 2, 8, 16, 32, etc. So each round there's an even number of competitors and never any buys. The maximum number of games in a double elimination tournament is 1 less than twice the number of teams participating. That's the maximum number of games, and that means that everybody loses 2 games except for 1 team. And so that's the maximum number of games, and the minimum number is 2 less than twice the number of teams. And for example, that would be if 1 team went undefeated through the entire tournament. Here's an example of a tournament bracket, and you see that this is a double elimination tournament, but this is for 7 teams, and so maybe by a draw or something like that, this number one team did get a bye. They didn't have to play in the first round. The other teams played, and then they engaged. And this seeding happens sometimes as well. Tournaments are excellent problems to ask questions about. This leads us to consideration of the multiplication rule. So suppose a computer installation has 4 input-output units. Think about these as being gateways or routers, and 3 CPUs, X, Y, and Z. These are called A, B, and C. And any output unit can be paired with any central processor. You could say I could reach any of the processors through any of these gateways. How many ways are there to pair input unit with output unit, or actually input-output unit with a CPU? And so we think about there being 2 steps. First, choose the input-output unit, and then choose the central processor unit. And notice that these are independent. So here are the possibilities. You see, you could get the input-output unit 4 ways, and then you could do 3. So it's 3 plus 3 plus 3 plus 3. 4 times 3 is 12. Now that is the fundamental idea behind this theorem, which is called the multiplication rule. It is a theorem, and you can prove this using induction. And here you would do this using induction on K. So anyway, let's talk about what the theorem says. If an operation consists of K steps, and the first step can be formed in N1 ways, and the second step can be formed in N2 ways, regardless of how the first step was performed, and ... means you keep doing that, and the kth step can be formed in N sub K ways, regardless of how the preceding steps were performed, then the entire operation can be formed in N1, N2, ... Nk ways, and that means you're multiplying these numbers together. To apply the multiplication rule, think of the objects you are trying to count as output of a multi-step operation. The possible number of ways to perform a step may depend on how many preceding steps were performed, but the number of ways to perform each step must be constant, regardless of the action taken in the prior steps. Please think about this. Let's do an example. This is where we're counting personal identification numbers, or PINs. So a certain personal identification number PIN is required to be the sequence of any 4 symbols chosen from the 26 uppercase letters in the Roman alphabet and the 10 digits. So the first question I ask is, how many different PINs are possible if repetition of the symbols is allowed? Well, if you start thinking about that, you could say, oh, I will fill 1 slot, 2 slot, 3 slot, 4 slot, in that order, and there's 36 ways I can do this because that's the pool of symbols that are available. But then there's 36 ways here, 36, 36, and so the answer is 36 raised to the 4th power, which is this big number. So there are many potential PINs. You might be thinking, well, yeah, but this is just kind of a made-up problem. Not at all. I worked for a company who was assigned to regulate the allocation of 800 telephone numbers, or toll-free telephone numbers. We had to do counting like this, and so it's a very real problem. Number B, how many different PINs are possible if repetition of symbols is not allowed? Well, okay, so again, you think of the PIN as being a 4-step process, but now you see the first one, and we're using this kind of idea of drawing a little places to put things. You can do 36, but then you have, once you pick that one, you only have 35, 34, and 33. You multiply those together, and you see that this number is less than that number. And the last question on this one is, what is the probability that a pin does not have a repeated symbol, assuming that all pins are equally likely? Again, these kind of problems are problems I could ask you on a test or a quiz. So let's see. So we know by part B there are this many pins that don't repeat. By part A, we know this were many, and so we can divide the 2, and we get that's the 4-digit approximation of the probability. So approximately 84% of the pins have no repeated symbol. Now you want to observe in that example that the set of all pins of length 4 is the same as the set of all strings of length 4, using a different vocabulary. And so S is the set of X such that S is a letter of the uppercase Roman alphabet, or X is a digit. Even another way to look at the pins of that example is as an ordered 4 tuple. That means you can think of a pin as M2ZM just as the ordered 4-tuple, but the order did make a difference. So this is the ordered 4-tuple that corresponds to that. Therefore, the total number of pins is the same as the total number of ordered 4-tuples whose elements are either letters or digit. And this is one of the most important uses of the multiplication rule, is to derive a general formula for the number of elements in any Cartesian product. Remember, that's what we studied in set theory, of a finite number of finite sets. And so let's look at this example. We're going to have 4 sets, A, B, or it's not A, B, it's A1, A2, A3, A4, and each of these sets have N1, N2, N3, N4 elements respectively. So we want to show that A1, the cross product, this is a set of 4 tuples, A1, A2, A3, A4 has this many elements. Well, you can think of this as 4 steps. Choose the first element, second element, third element, and fourth element. And that means you're going to multiply N1 times N2 times N3 times N4. And that's those are the distinct number of 4 tuples in this Cartesian cross product. Let's look at a different example of counting. This is the number of input-output tables for a circuit. You could think about this as being a computer logic circuit with 2 input signals. Okay, so we're going to consider all circuits with 2 input signals. That means you have a lead coming in that's a P and another lead coming in that's a Q. Each of these can be a 1 or a 0. And so how many distinct output tables are there? Well, fix the order of input for P and Q. Then there are 2 input-output tables are distinct if their input-outputs are different in at least 1 row. And so here are 2 that are distinct because their output values differ in the first row. So this is 2 of them, and there are more. So for a fixed ordering of the input values, which you can do, you can obtain a complete input-output table by filling in the entries in the output column. You can think of this as a 4-step operation. So we can fill in the output value for row 1, then we can fill in the output value for row 2, row 3, and row 4. That means that we have 2 times 2 times 2 times 2 equal 16 ways to perform the entire operation. It follows that there are 16 distinct input-output tables for a circuit with 2 input signals. This means that such a circuit can function in 16 distinct ways. Again, it doesn't have to be the truth table formulation. It can be something different. Also observe that another way to think of this example is to realize that there are as many input-output tables for a circuit with 2 inputs as there are bit strings of length 4, written vertically. And those are vertical, and here we're writing horizontally. And so another way to think about this is another example, I guess I should say. Here is a listing of all bit strings of length 3. So you see, you fill those out, and that's going to be the listing of all those bit streams. And you can see there are 3, 3, and 2, and that's going to be 6. Or you could say 2 times 2 times, that's not 6, that's 8. So there's 3, 6, and 2 is 8, and 8 is also 2 ways to fill the first one, 2 ways to fill the second one, 2 ways to fill the third one. Let's talk about software now. We've talked about hardware a bit. Let's talk about software. Consider the nested loop in a program. And so the program, and this is written in pseudocode, but for I equaling 1 to 4, but nested inside of that is a do loop that says for j equaling 1 to 3, and there's some statements in the body of this inner loop. Now, none of these statements contain branching statements that lead out of the inner loop, or else this count is fraudulent, but programming a lot of times happen this way. And so what you do is you have, this is the next j, you increment that, and then on the outside of that, you increment the I. So the question that I'm posing here, another good exam question, is how many times will the inner loop be iterated when the algorithm is iterated and run? And the solution is the outer loop is iterated 4 times, and during each iteration of that, the inner loop has 3 iterations. So the answer is 4 times 3, and here is a trace table shown down here for i's and j's, and you can count that, and you will get 12 for that. Now, sometimes the multiplication rule is difficult or perhaps impossible to apply, and consider the following problem as an example. We have 3 officers: a president, a treasurer, and a secretary are to be chosen from among 4 people: Ann, Bob, Sid, and Dan. Suppose that, for various reasons, Ann cannot be president, and neither Sid nor Dan must be the secretary. And either Sid or Dan must be the secretary. How many ways can the officers be chosen? Now, it's natural to try to solve this problem using the multiplication rule, and here's a way to think of it. And if you thought about that, you could say, oh, there's 3 ways times 2 ways, 18 choices. But unfortunately, that is incorrect, because the number of ways to choose the secretary varies depending on who is chosen for president and treasurer. For example, if Bob is chosen for president and Ann for treasurer, there are 2 choices for secretary. But if Bob is chosen for president and Sid for treasurer, there's only 1 choice, Dan. So the clearest way to do all this is to construct a possibility tree, as we show here. And we're choosing the president in step 1, then we're choosing the treasurer, and finally we're choosing the secretary. And it's easy to see there are only 8 ways to complete this choosing a president, treasurer, and secretary, and not as many as we talked about before. Now, another way to solve this problem, though, should be considered, and it's somewhat surprising. It turns out that the steps can be reordered in a slightly different way, so the number of ways to perform each step is constant, regardless of the previous steps performed. And this is more subtle, but we're going to reorder this, and first we're choosing the secretary, then we're choosing the president, then we're choosing the secretary. And you see each step, in this case, has only 2 possibilities, so it is 2 times 2 times 2, and so we do get the answer of 8 correctly if we use this more subtle use of the multiplication rule. This leads us to consideration of a mathematical formula, a mathematical function called permutations. A permutation of a set of objects is an ordering of the objects in a row. For example, if we were talking about the set of elements A, B, C, there are 6 permutations. These are all different because order matters. In general, given a set of n objects, how many permutations does a set have? Well, you can think about that as being an in-step operation. You choose an element first, and then you choose an element B second, and so on and so forth. Now, any element of the set can be chosen in step 1, so there are n ways to do that, but then we can't reuse that in a permutation, so that means there's n minus 1 ways to do the next one. And so you see, if we just drew the little slots where we were putting things, there'd be n ways for this one, n minus 1 for that one, n minus 2 for that one, dot, dot, all the way down to 1. This is n factorial. We talked about the definition of factorial before. So you see there are n factorial ways to perform this operation that we spoke of up here. In other words, there are n factorial permutations of a set of n elements. And we quote that as a theorem here, and I'm stating it again. For any integer n bigger than or equal to 1, the number of permutations of a set with n elements is n factorial. And this would be proven by mathematical induction. If you needed to prove it, you might say you're willing to take this on faith. Let's apply that to some problems. So we'll say, how many ways can the letters in the word computer be arranged in a row? And notice that all of these letters are distinct one with another. And so what happens is there are 8 distinct letters. That means the answer to that is 8 factorial ways, and it's a little better than 40,000. I would expect you to probably give me this number as an answer. I'm changing the problem now. In how many ways can the letters in the word computer be arranged if the letters CO must remain next to one another as a unit? Well, the cleverest way to do this, say they have to remain next to each other in that order. So really, I don't have 8 choices. I have this, and the CO moves as a block. So there are 7 factorial ways for this to happen. Much fewer, because I'm saying that has to be in block. And lastly, in this example, if the letters of the word computer are randomly arranged in a row, what's the probability that the CO remains next to each other in order as a unit? Well, I just take the quotient of the answer from B with the answer from A, and I get it is 1 over 8, or exactly in this case, 12.5%. Things are a little different if we talk about permutation of objects around a circle. So at a meeting of diplomats, 6 participants are to be seated around a circular table. Now the table has no ends to confer a particular status, so it doesn't matter who sits in which chair, but it does matter how the diplomats are seated relative to each other. In other words, 2 seatings are considered the same if one is just a rotation of the other. How many different ways can the diplomats be seated? Okay, so for sake of the discussion, let's call the diplomats this instead of giving them names. So you can start the diagram anywhere with, say, A, but then you have to place then that places the diplomat anywhere, say at the top of the diagram, and that's what we're showing here, but it's really anywhere. So the 5 diplomats, B through C, can be arrangements of other diplomats around that one. So the 5 diplomats, B through F, rather, can be arranged in the seats around diplomat A in all possible orders. So you see there were 6 to start with, sort of 5 factorial ways to seat them. And you could say we will always go clockwise, so there's 5 ways to do this, 4 ways to do that, and so on and so forth. So 5 factorial is 120. We can also talk about permutations of selected objects, and these will be not always taking all of the objects. So given a set ABC, there are 6 ways to select 2 letters from this. They're listed here, and again, order matters. So each such ordering of 2 elements of a set consisting of 3, ABC, is called a 2 permutation of ABC. And here's the more general definition of that. An R permutation of a set of n elements is an ordered selection of R elements. Order matters, taken from the set of n elements. The number of R permutations of a set of n elements is denoted P in R. And we'll talk about other notations. Sometimes this is said, quoted a different way. We'd say n permutations take an R at a time. It depends a little bit on the notation. So here's the theorem for that, and what we're going to see in the theorem is that if n and r are integers and r is less than or equal to n, and you have to, check all of those things, or address all of those numbers in your proof, then the number of r permutations of a set of n elements is given by the formula. Well, the first thing you could do is you say, well, I'll just make those little lines, and there's n ways to do the first one, there's n minus 1 ways to do this second one, and then there's n minus 2 ways, given those assignments, to do it, and all the way down, and you stop at n minus r plus 1. But equivalently, what I can do is multiply top and bottom by the same number. That's something mathematicians often do. So this, if I multiply top and bottom by n minus r factorial, top and bottom, I'll end up with this formula. And that, in fact, is, it says or equivalently, and that's the second version. And this is what typically is written as a math formula for the permutations. And we talked about the proof. I said you line up these positions, you count them, and you get this, and but it can be written this way. So there's a formula, and you would prove this by induction on n. But let's evaluate some of this. So here we're evaluating 5 permutations, take it 2 at a time. We just use the formula, and you should get 20. Notice the 3 factorials cancel. How many 4 permutations are there in a set of 7 objects? Well, that's going to be P, 7, 4. Here's the calculation. Again, the 3 factorials cancel. You get 840. The number of 5 permutations of a set of 5 objects, we do that. And notice that we're using the fact, and we talked about this before, that 0 factorial is defined to be 1. You can also make an argument that it should be 1, but 0 factorial is 1. So this is 5 factorial. This is 120. Let's do a different example. Now we're talking about permutations of selected letters of the word. So now we're talking about the word bites. and this is BYTES, and that stands for, those are computer bytes. We'll talk more about that later in the course. How many different ways can 3 of the letters of this be chosen and written in a row? And you see, so order matters, and you should realize that this has 5 distinct things. So this is going to be 5 permutations, because order matters, taken 3 at a time. Here's the formula. We plug it in. Notice that the 2 factorials cancel, and you get 60. Part B says, how many different ways can this be done if the first letter must be B? Well, the first letter is fixed to be B. I only get to choose the next 2, and I'm choosing them from this because I can't repeat the B. So this is going to be 4, because I have 4 up here, and I'm 4 permutations taken 2 at a time. I do the calculation, and it is 12. In many applications of mathematics of counting, it's necessary to be skillful in working algebraically with quantities of the form P permutations taken R at a time. That's what's in our next example. So I could ask you to prove this. Prove that for every integer n bigger than or equal to 2, n permutations taken 2 at a time plus n permutations taken 1 at a time is equal to n squared. Okay, so suppose that we're greater than or equal to 2. I'm going to just take this term. I'm going to write what it is, and I get n times n minus 1. And I'm going to figure out what this term is. I will use the definition. I'll find that n. So now I say, what happens when I add those 2 together? So I'm adding n times n minus 1 plus n. I get n squared. I'm distributing here, so it's n squared minus n and plus n. So those will cancel out, and I get n squared, which is exactly what we needed to show. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.